All right, today we are diving into a real classic physics problem, the conical pendulum. Now, if you're one of the many people who's found rotational motion kind of confusing, stick around. We are going to break this thing down step by step, and in the process, we're going to uncover a really core concept in mechanics. But first, let me hit you with a bit of a paradox. Is it possible for something, let's say a vector, to be constant in size, its magnitude doesn't change, but at the same time, it's always changing? I mean, that sounds completely impossible, right? Just keep that question tucked in the back of your mind, because the answer is actually the key to unlocking this whole problem. So here's the beast itself, straight out of the legendary I.E. Irodov problem book, which if you know it's tough stuff. It's asking us two main things. First, where, relative to what points, does the ball's angular momentum stay constant? And second, what's the actual change in that angular momentum relative to the suspension point O after the ball goes halfway around the circle? To figure this out, we first need to lay down the rules of the game. Yeah, before we can even think about solving this, we need to be absolutely crystal clear on the rules of rotational motion. And that means we need to understand the two key players in this whole drama: angular momentum and torque. First up, we've got angular momentum. We'll call it M. Think of it like this. You know how regular linear momentum is an object's tendency to keep moving in a straight line? Well, angular momentum is its tendency to keep spinning. It's basically the amount of rotation something has. And here's the really crucial part. It's a vector. That means it has a size or a magnitude, and it has a direction. Both matter. So if angular momentum is the motion itself, what causes that motion to change? Well, that's torque, which we'll call N. It's the rotational version of a force. It's not a push or a pull, it's a twist. If you want to change how something is spinning, you need to apply a torque. It's that simple. And that brings us to the golden rule that connects them. It looks a little scary, but it's not, I promise. It just says that the net or total external torque on a system is equal to the rate of change of its angular momentum. Now, the implication here is absolutely key to our whole problem. If the net torque, N, is 0, then the rate of change, dm by dt, also has to be 0. And what does that mean? It means the angular momentum vector, m, doesn't change at all. It stays constant. Okay, so armed with our golden rule, let's play detective and solve the first mystery. For our conical pendulum, we just need to find the point where the net torque is 0, because that's where the angular momentum is going to be constant. The most obvious place to start is the suspension point, O, right? Where the thread is tied to the ceiling. So to find out if angular momentum is constant relative to O, we just have to ask one simple question. Is the net torque about point O equal to 0? Let's break down the forces acting on the ball. We've got the tension in the thread, T, and we've got gravity, mg, pulling it down. Now, think about the tension force. It's always pulling directly through our pivot point, O. A force that goes right through the pivot point has no leverage, right? It can't cause a twist. So tension creates 0 torque. That one's out. But what about gravity? It pulls straight down. The position vector r from O to the ball and that downward force of gravity are not lined up. So when you take their cross product, you get a non-zero torque. It's a horizontal twist that's always trying to pull the pendulum down. So here's the verdict. Because there is a net torque about point O, thanks to gravity, our golden rule tells us the angular momentum vector m is not constant. It has to be changing. So mystery number 1 isn't solved just yet. Okay, if not the suspension point O, let's try another spot. What about the dead center of that horizontal circle the ball is tracing out? Let's call that point C. Is the angular momentum vector constant when we measure it from there? Let's really think about the angular momentum vector m from this new point, C. Remember, m comes from the cross product of the position vector r and the momentum vector, p. From point C, the position vector rc is just the radius of the circle, always pointing horizontally from the center to the ball. The momentum, p, is the direction of travel, always tangent to the circle. Now, if you use the right-hand rule for the cross product, you'll find something cool. The resulting vector, m, always points straight up. Its direction never ever changes. And since the problem says the ball moves at a constant speed, the magnitude of m doesn't change either. So what do we have? A vector with a constant magnitude and a constant direction. And that, my friends, is a truly constant vector. And there it is, the answer to our first mystery. The angular momentum of the ball is constant relative to the center of the circle, C. One mystery down, one to go. So we cracked the first case. But now we have to tackle the second part of the problem. We need to find the actual change in angular momentum. We'll call it delta M, relative to that original suspension point, O, after the ball swings through half a revolution. Now, wait a second, you might be thinking, didn't we just prove that M is not constant about point O? And you're right, we did. But just because it's changing doesn't mean we can't calculate how much it changes. Our mission is to find that change, delta M. And that's just the final angular momentum vector minus the initial one.
And this is where we finally solve that paradox from the beginning. Relative to point O, the magnitude, the length of the angular momentum vector is actually constant. But remember that pesky torque from gravity? That torque is constantly nudging the angular momentum vector, forcing its direction to change. As the ball goes around, the M vector actually sweeps out a cone. So you see, the vector's length stays the same, but it's constantly changing because it's always pointing somewhere new.
Let's just visualize this to make it super clear, okay? At our starting point, let's say the ball is at the front of its circle, moving to the right. The angular momentum vector, M initial, is perpendicular to both the thread and the motion, so it's pointing up and to the left, just like you see here. Okay, now let's go halfway around the circle. The ball is on the opposite side, now moving to the left. The new angular momentum vector, M final, still has the exact same length, but look, now it's pointing up and to the right. So how do we find the change, delta M? Well, we use vector subtraction, M final minus M initial. Now graphically, subtracting a vector is the same as adding its opposite. So we start with our final vector, M final. Then we take our initial vector, flip it around 180 degrees to get negative M initial, and place its tail at the tip of M final. The vector that connects the very beginning to the very end, that's our answer. That's delta M. And as you can see, it points horizontally straight across. And the magnitude, the size of that final vector, delta M, can be calculated. When you work through the geometry and the physics, you find that its magnitude is equal to 2 times the mass, times the length of the thread, times the angular velocity, times the radius of the circle. And just like that, our second mystery is solved. Okay, we did it. We solved a pretty tough problem. But what's the point? What did we actually learn here that we can use on other problems? Let's boil it all down into a quick cheat sheet for rotational motion. Here are the 4 big lessons. Number 1, the pivot point is everything. Where you choose to measure from completely changes the problem. Angular momentum was constant about C, but it was a changing mess about O. 2, torque is the agent of change. If you want to know if angular momentum is conserved, just find the network. If it's 0, you are golden. 3, the big one, constant magnitude does not equal a constant vector. That paradox is solved. Direction matters just as much as size. And finally, number 4, when in doubt, visualize it. Drawing out those vectors made the subtraction process a million times clearer than just staring at an equation. So that's our deep dive into the conical pendulum. But hey, I want to leave you with a final brain teaser. We assumed our thread was massless, totally idealized. But what if it wasn't? What if the thread itself had mass? How would that change the torques, the angular momentum, and our final answer? That's something to chew on. Thanks for joining me for this one.